Where do forces come from? The birth of gauge symmetry. We experience forces every day. Push a door and it opens. Throw a ball and it flies through the air. Magnets attract iron and Earth keeps us firmly on the ground. Inside an atom, electrons remain bound to the nucleus. And inside the nucleus, protons and neutrons are held together by an even stronger interaction. So naturally, we tend to imagine a force as something that pushes or pulls one object from a distance. But modern physics tells a very different story. Electromagnetism and the nuclear forces may not be invisible ropes stretched between particles. They may be the consequence of nature trying to preserve a deeper rule. That rule is called symmetry. When we hear the word symmetry, we usually imagine a perfectly balanced face, a butterfly's wings, or a circle that looks the same from every direction. But in physics, symmetry means something much broader. A symmetry exists when we change something about our description of nature, yet the laws of physics remain unchanged. Imagine moving a laboratory experiment from Seoul to New York. If the experimental conditions are the same, the properties of an electron should not suddenly change. A law that works today should not fail tomorrow for no reason. And rotating an entire experiment should not alter the electric charge of a particle. If the laws remain the same when we change location, time, direction, or reference frame, we say that nature possesses a symmetry. Surprisingly, symmetry is not merely an aesthetic decoration added to physical laws. It explains why important quantities are conserved. Because the laws of physics do not change with time, energy is conserved. Because the laws do not depend on where an experiment is performed, momentum is conserved. Because the laws remain the same when we rotate a system, angular momentum is conserved. Behind every major conservation law, there is a symmetry. So we may ask a deeper question. Could symmetry also lie behind the forces of nature? To answer that, we must step inside the quantum world. An electron is not simply a tiny metal ball. In quantum mechanics, an electron is described by a wave function. This wave function contains not only an amplitude, but also something called phase. Phase tells us where a wave is within its cycle. It acts like an internal clock. Imagine two people singing the same song. One begins exactly on the first beat, while the other starts half a beat later. They are singing the same melody, but their phases are different. For waves, this difference matters. When two waves are in phase, they can reinforce one another. When they are out of phase, they can partially or completely cancel. Quantum mechanics gives us an interesting freedom. If we change the overall phase of a particle's wave function everywhere by the same amount, no measurable result changes. It is like shifting every number on every clock by 1 hour while leaving all time differences unchanged. This freedom is a symmetry. We can change the internal phase convention of an electron, and the observable laws of physics remain the same. So far, this is relatively straightforward. The real challenge begins when we allow the phase convention to change differently from place to place. Suppose that in Seoul, we set an electron's internal clock slightly ahead. In Busan, we set it slightly behind. On Jeju Island, we choose yet another convention. Can every location choose its own phase reference while the laws of physics still remain consistent everywhere? This is the central question of local gauge symmetry. The word local means that the choice may be made independently at every point in space and time. In a global symmetry, we change the phase convention everywhere by the same amount. In a local symmetry, each point is allowed to choose a different convention, and that creates a problem. At a single point, the choice of convention may not matter. But when we compare states at two different points, we must know how their conventions differ. Consider clocks in Seoul, London, and New York. Each city is free to display its own local time. But if we want to compare two events that occur in different cities, we need information about the time zone difference. Currencies provide another example. Korea uses the won, while the United States uses the dollar. Each country is free to use its own currency unit. But to compare prices, we need an exchange rate. Quantum phase works in a similar way. If each point in space is allowed to choose its own phase convention, we need a new structure that tells us how to compare those choices from one point to another. Modern physics calls this connecting structure a gauge field. A gauge field tells us how internal reference standards vary across space and time. And in the case of electromagnetism, that gauge field is the electromagnetic field. This point is crucial. Physicists did not simply assume that the electromagnetic field existed and then adjust the symmetry afterward. The logic works in the opposite direction. We require the laws of physics to remain unchanged even when the phase convention is chosen independently at every point. Once we make that demand, an electromagnetic gauge field becomes necessary. In other words, if nature permits local freedom in choosing internal standards, it must also provide a field that connects and compensates for those choices. When that field interacts with charged particles, we experience the result as a force. Electromagnetism is therefore more than a mysterious attraction or repulsion between charges. It can be understood as the structure required to compare quantum phases consistently across space. Let us use a more familiar analogy. Imagine musicians in different cities attempting to perform together over the internet. Each musician follows the same score, but network delays cause their timing to drift. Even if every player performs correctly in isolation, the combined music can become chaotic. To create a coherent performance, they need a synchronization signal that constantly tracks and corrects their timing differences. Without that signal, local freedom destroys global harmony. A gauge field plays a similar role. It allows each point to choose its own internal convention while preserving consistency between neighboring points. The quantum particle associated with the electromagnetic field is the photon. The light we see is made of photons, but photons are more than particles of visible light. At a deeper level, they are the gauge bosons that mediate electromagnetic interactions between charged particles. A gauge boson is a particle associated with a gauge field. For electromagnetism, that particle is the photon. But nature contains more than electromagnetism. Inside atomic nuclei, the strong interaction binds quarks together. Radioactive decay and nuclear reactions in the sun involve the weak interaction. The gauge symmetry of electromagnetism is comparatively simple. It concerns a single-phase convention, which can be pictured as a rotation around a circle. The order of these phase rotations does not matter. But the weak and strong interactions require more complex symmetries. Instead of changing a single phase, several internal particle states can mix and transform into one another. In the weak interaction, states such as electrons and neutrinos are connected within a shared structure. In the strong interaction, quarks possess three types of color charge, conventionally called red, green, and blue. These are not literal colors. They are names used to distinguish three internal quantum states. In these more complex symmetries, the order of transformations matters. Imagine holding a smartphone. Rotating it sideways and then flipping it may produce a different final orientation from flipping it first and rotating it afterward. When changing the order of transformations changes the result, the symmetry is called non-abelian. The symmetry of electromagnetism is abelian. The order of transformations does not matter. The symmetries of the weak and strong interactions are non-abelian. Their transformations do not generally commute. This mathematical distinction produces major physical consequences. The photon carries no electric charge. As a result, photons do not normally interact strongly and directly with one another. But gluons, the particles that mediate the strong interaction, carry color charge themselves. This means gluons interact not only with quarks, but also with other gluons. That is why the strong interaction is much more complicated than electromagnetism. When we try to separate quarks, the force between them does not become weaker. It becomes stronger. Eventually, instead of extracting a single quark, enough energy is stored in the field to create new particles. This is why isolated quarks are not observed under ordinary conditions. They remain confined inside composite particles such as protons and neutrons. This phenomenon is called quark confinement. Electromagnetism, the weak interaction, and the strong interaction appear very different. Yet all three are described using the common language of gauge symmetry. Electromagnetism has one type of gauge structure. The weak interaction involves 3 gauge directions. The strong interaction involves 8 gauge fields, corresponding to 8 types of gluons. Before the middle of the 20th century, particle physics often seemed like the study of an ever-growing list of new particles. Electrons, protons, neutrons, muons, pions, kaons, and many other particles were discovered. So many appeared that physicists began calling the collection the particle zoo. The challenge was to find a small number of principles capable of organizing this apparent chaos. In 1954, Chen-Ning Yang and Robert Mills extended the gauge principle of electromagnetism to more complex internal symmetries. At first, Yang-Mills theory appeared to be mathematically elegant, but physically difficult to apply. The main problem was mass. A strict gauge symmetry seemed to require the force-carrying particles to be massless. The photon is indeed massless, but the particles responsible for the weak interaction are very heavy. If Yang-Mills theory was to describe the real world, physicists needed a way to generate mass without destroying the gauge structure. The solution eventually came through spontaneous symmetry breaking and the Higgs mechanism. Once that problem was resolved, Yang-Mills theory became the central framework for describing both the weak and strong interactions. Today, the standard model explains electromagnetism, the weak interaction, and the strong interaction as gauge theories. Electromagnetism is associated with one symmetry. The weak interaction is governed by another, and the strong interaction is based on a symmetry that mixes the 3 color states of quarks. Together, these gauge structures form the backbone of the standard model. But what about gravity? Gravity is different. In general relativity, gravity is not treated as an ordinary force acting between objects. It is described as the curvature of space-time itself. Even so, general relativity also contains deep forms of local symmetry and freedom in choosing coordinates and local frames. For this reason, many physicists have searched for a more fundamental principle that could unify gravity with the other interactions. Grand unified theories, supersymmetry, string theory, and loop quantum gravity all approach this problem in different ways. But no experimentally confirmed theory yet unifies electromagnetism, the weak force, the strong force, and gravity into one complete framework. Here we arrive at one of the deepest philosophical lessons of gauge symmetry. In classical thinking, objects come first, and forces act between those objects. But in gauge theory, relationships may be more fundamental. The absolute phase of an individual particle is not directly observable. What matters is the difference between phases and the way states at different locations are connected. A force may therefore be less like a property attached to an isolated object and more like a structure that preserves consistency among relationships. This relational viewpoint appears throughout modern physics. In quantum mechanics, interference and relative phase matter more than an absolute wave phase. In general relativity, space-time relations between events matter more than an absolute background space. In gauge theory, the connection between local reference choices matters more than any single choice by itself. And this leads to a new question. Could something similar apply not only to electric charge or color charge, but also to information? Could the way quantum states are prepared, aligned, entangled, and transported through space and time possess its own local reference structure? Could information be more than a description used by an observer? Could it participate directly in physical dynamics? Information gauge theory, or IG theory, begins from this possibility. In established gauge theories, electrically charged matter couples to the electromagnetic field. Quarks carrying color charge couple to gluon fields. IG theory explores whether information flow, information state alignment, or entanglement structure might couple to an additional information gauge field. Of course, this is not an established theory like the Standard Model. At present, it remains a research hypothesis that requires a precise mathematical formulation and experimental verification. But historically, the question itself is not unreasonable. The electromagnetic field was once an unfamiliar invisible entity filling space. Yang-Mills theory initially appeared to be abstract mathematics with little direct connection to reality. The important issue is not whether a new idea sounds strange. The important questions are whether it is mathematically consistent, whether it produces new predictions, and whether it can be proven wrong by experiment. For IG theory to have physical meaning, it must predict concrete deviations that cannot be explained by known electromagnetism, gravity, or environmental effects. Could atomic spectroscopy reveal extremely small frequency shifts associated with the way a quantum state was prepared? Could different entanglement structures produce measurable phase differences? Could Josephson interferometers display an additional phase offset linked to non-equilibrium information flow? Could the growth of cosmic structure show patterns that differ from the predictions of standard gravity and dark matter? Without observable signatures, the idea of an information gauge field would remain a philosophical metaphor. But if a clear and repeatable signal were discovered, the history of gauge symmetry might enter a new chapter. We began with a simple question. Where do forces come from? Classical physics says that objects with mass or charge exert forces on one another. Modern particle physics goes one step deeper. It requires that the laws of nature remain unchanged even when internal reference conventions are chosen independently at every point in space and time. That requirement creates the need for gauge fields connecting those local choices. In electromagnetism, the photon plays this role. In the weak interaction, W and Z bosons mediate the connection. In the strong interaction, gluons connect the color states of quarks. From this perspective, forces are the connecting structures required for nature to preserve local symmetry. But one major problem remains. If gauge symmetry is exact, force-carrying particles appear to need zero mass. The photon is indeed massless. Yet the W and Z bosons are extremely heavy. How did nature give particles mass without abandoning gauge symmetry? The answer lies in a field that fills the entire universe, even what we normally call empty space. That field is the Higgs field. In the next episode, we will explore how gauge symmetry and the Higgs field combine to create the Standard Model, and why even this extraordinarily successful theory still fails to explain most of the universe. Thank you for watching this video. This is ThothSaem Physics.